This video is my third example of an improper integral. I'm going to try to compute this. I assume you have watched the previous two videos in which I define improper integral and I explain how to compute them. If so, I invite you to pause this video and try to get the answer before continuing. In this example, I want to calculate the integral between 0 and infinity of sine of x with respect to x. This is an improper integral because the domain goes all the way to infinity. Geometrically, this represents the area between the graph of sine and the x-axis, except that the pieces of the region that are above the axis count as positive, and the pieces that are below the axis count as negative. If we don't think about it too carefully, it may look like the answer is going to be 0, because every positive region is going to cancel exactly with a negative region. But that could be incorrect. Let's actually do it from the definition and see why that's not the answer. According to the definition of improper integral, the way they integrate all the way to infinity is to first integrate to a number which I'm going to call b, the same function, and then take the limit as this number goes to infinity. So first perform the integral and then take the limit. But before I do it, let's try to guess now from the definition what we want the answer to be. Each one of these regions has the same area by symmetry. That area turns out to be 2, but even if I didn't know that, I know they all have the same region. So if I take the integral from 0 to here, it's going to be 2. This area is 2. And if I take the integral from 0 to here, then it's going to be 0 because they cancel. Now if I integrate from 0 to here, it's going to be 2 again. And from 0 to here is going to be 0. If I keep doing that, the integral from 0 to b, as I make b grow and grow bigger and bigger, is going to oscillate between 2 and 0, 2 and 0, 2 and 0. It looks like this limit is not going to exist. Okay, that's the geometric approach. Let's verify that the algebra gives us the same result and that the definition is good. First, I need to find an antiderivative for sine x, but I know how to do that. An antiderivative of sine x is minus cos x, and then I need to evaluate at 0 and at b. So I get the following limit. Cosine of 0 is actually 1, and as b approaches infinity, cosine of b does not have a limit, because this function oscillates between minus 1 and 1 indefinitely. So the sum of the two things actually oscillates between 0 and 2, exactly as I expected. So this limit does not exist. And the original integral happens to be divergent. This integral is not a number. It is not infinity and it is not minus infinity. It's simply not well defined. It doesn't represent anything. It is divergent.